Hi everyone, I'm going to make a video on inorganic chemistry. This is chapter 2, and this is going to be the first part of this chapter. I would like to get a pointer here. Give me one moment. All right, and then I'm going to expand my PowerPoint. Okay, so in the beginning here, of chapter 2, I've gathered some images so you can see how important this chapter is and how it applies to everyday life. Okay, so other fields besides anatomy and physiology. So let's see. In here, in the beginning, I talk about. First of all, I want to make you aware of a YouTube video that I have here. This YouTube video is called the Pale Blue Dot. I don't know if you ever heard about that, but that was a video that was created by Carl Sagan. Carl Sagan, he talked about Voyager. This is a spacecraft or a space probe that was sent from the Earth into outer space, and it's still functioning. Okay, Voyager 1 and then Voyager 2. And so now right now, I think Voyager 1 is at a distance of 24 billion miles from Earth. And in this video, the pale blue dot, as Boyer was at a certain distance from the Earth, he asked that to turn on the camera and to turn towards the Earth, and he showed a pale blue dot, and then he mentions that is us. We live there. There is civilization there, and sometimes as we look to the sky and we see pale blue dots out there, we are uncertain whether there is civilization. So I urge you to actually see this first video here, okay, about the pale blue dot and Carl Sagan, and basically also in this video he mentions about that the Earth is the only place we know where life can exist, and we need to take care of this planet, and we need to get along with each other, because through many generations, there has been a lot of wars, where people have killed each other just to gain a little territory, a little part of or a pixel of the Earth. Okay, so I think it's very interesting, to watch that video. The other videos are more like whether we have been in the moon or not. There's conspiracy theories about whether that actually happened. And kind of like now that you watch the Elon Musk with his rockets, we see how difficult it is to accomplish that task. You're probably asking yourself, how is these spacecraft or space probes are still functioning and transmitting signals? What type of energy do they have? And this is basically nuclear energy. So we have nuclear batteries, and basically radioisotopes. This is a topic that we're going to be discussing soon. As they decay, they emit heat, and heat is converted to electrical energy. And it's kind of interesting, that concept, but this will give a lot of durability, for these spacecraft to work. Here is a planetarium that we have here at Indian River State College. Okay, and I think it's very interesting, and you should go there and learn a little bit about astronomy, and and so there is a lot of applications, of this information, not just in our field, but in other fields, like in astronomy for deep space exploration. And there were previous probes that were sent before. One was in 1972, 1973, and they traveled I think past Saturn. But Voyager has actually been the furthest, spacecraft that has traveled away from the Earth. And now 2006 they sent another one which is called I think it was like New Horizon, was sent in 2006, and that one it's the speed of these probes. I mean, Horizon, the one that was just sent, is going to have higher speeds than Voyager. Voyager 1, the speed is about 36. I think I have it somewhere in here. Sometimes I do write notes right underneath here. But you can see that if I just open up here, so it's like 38,000 miles per hour. That's the speed that it's traveling. And Voyager 2 has a speed of 35,000 miles per hour. By New Horizons, it's the initial speed is 36,400 miles per hour. And now it's going to be way more once it passes Jupiter and then later Saturn. There is a sort of like they talk about here, that they get a gravity assistance, from Jupiter and Saturn. And this, so there is like some type of force that will propel them, push them at a much higher speeds. So this is a really interesting topic, to say the least. For us, I think, we just need to, from the beginning here, from the get-go, we need to know two facts here. We need to know that oxygen is the most common element in the human body, that it comprises approximately 65% of our body mass. And also we need to know that calcium is the most abundant mineral in the human body. Notice that they talk about mineral, and they talk here about element. Okay, we have the periodic table of elements, and we see oxygen and we see also calcium. But a lot of times students can misinterpret the situation, the information. So it's important that you are awake and alert about how you interpret or read the information. Because if they say element, that will be oxygen, the most abundant, the most common element. But the most abundant mineral will be calcium. Okay. And here's the periodic table of elements. Periodic table of elements, and in here we see the element symbol and the name of the element. Here we have sodium. So sodium is represented as Na. Notice that it's all of these elements are organized based on their atomic number. So the atomic number for sodium is 11, and you see that it's here, 11, right? And notice also that these colors, they represent the what type of element this is. Okay, sodium is considered an alkali metal. Okay, and so sodium, notice that it has the atomic number of 11. The atomic number is the number of protons of an atom. Okay, so sodium has an atomic number of 11, so it has 11 protons. Okay, notice that hydrogen has 1 proton, so that's the atomic number is 1. Okay, then helium is number 2, and then lithium is 3, and beryllium is 4, and you go all across here. I think we have to pay attention. The most common ones that we need to know, like for example, sodium, we need to know that it's on this side of the periodic table, okay? It is a metal, okay? Now we can also, oops, what happened here? I think I clicked on something and it took me someplace else, sorry. Okay, so we can also see carbon. You know, carbon has an atomic number of 6. Nitrogen has an atomic number of 7, okay? And oxygen has an atomic number of 8. You can see chlorine here, it's 17. So, you know, carbon, nitrogen, oxygen, chlorine, that's sodium. You know, we need to keep an eye on those, okay? Down below, you can see the atomic weight, and for sodium is 22.9, about 23 is the atomic weight. 23 is about the atomic weight of sodium. So let's continue. Okay, so let's talk about atomic structure. So first, we need to know what an atom is. So an atom is the basic unit of matter, okay? And when we study an atom, we see that there is a nucleus on the inside, right? A nucleus. And this nucleus is surrounded by electrons. Electrons are negatively charged, okay? So we call this the electron cloud, okay? And in the nucleus, we can find protons and we can find neutrons, okay? And notice in here that hydrogen-1 doesn't have any neutrons, but hydrogen-2 has 1, and hydrogen-3 has 2 neutrons, okay? So, so these are all variations, you know, variations of an atom. And variations of an atom, basically we call them isotopes, right? So atoms of an element who have the same number of protons but different number of neutrons, we refer to them as isotopes. You do need to know the definition for isotopes. Okay, so and remember that in the nucleus of an atom, the nuclear number, right? In the nucleus of an atom, we can find protons and we can find neutrons. Okay, so see that? So hydrogen-1 is the only stable nuclide with no neutrons. So let's continue. So atomic number, we're looking here at helium. Okay, atomic number is represented by the letter Z. I'm not going to ask you about that. The atomic mass number is represented by the letter A. I'm not going to ask about, you know, what A represents or C represents, Z represents. But you need to know that the atomic number refers to the number of protons. And that's how we organize the element, how the elements of an atom are organized in a periodic table. So you can see here that helium has an atomic number of 2, okay? And that means the number of protons. And those, you can see that the protons are positively charged, right? So we have 2 protons in the nucleus here. All right, and now this number up here is called the atomic mass number or nuclear number. And that represents the number of protons and the number of neutrons. And that's 4. We see that here, okay? So, so you can see that the atomic number is basically, you can see here that actually, if you want to know the nuclear, the number of neutrons, sorry, you'd have to subtract the atomic number from the atomic mass number. I mean, the atomic mass number, you have to subtract that from the atomic mass number. You get the number of neutrons. But this is helium. Okay, another thing that we can see here with helium is that it has 2 protons. So if an atom has 2 protons, it must have 2 electrons. Okay, so these, and by the way, this first cloud of electrons here, this first energy level is can be occupied by 2 electrons. So you can see that this shell here, this energy level, is filled. So this, so helium is a noble gas. So it tends to not react. Okay, and you can see that in the periodic table, the noble gases are over here, and we can see helium all the way here with an atomic number of 2. Okay, the atomic mass number of 4. All right, so let's continue. Now, isotopes. So isotopes, again, are atoms of the same element whose nuclei contain the same number of protons, but different number of neutrons, okay? And we saw that with the element of hydrogen, that there are variations of this element, okay? And we call these isotopes. You can also say that an isotope or isotopes are atoms of the same element with the same atomic number but different mass number. Okay. When we talk about isotopes, we always talk about, like, as an example, carbon-14. Carbon-14, by the way, the most common the most common atom or isotope, for example, of the most common isotope of carbon is carbon-12. Okay, but here's the atomic weight. The atomic weight that we saw in the periodic table. In the periodic table, we saw the atomic weight. The atomic weight is the average atomic mass of the isotopes. Okay, so the average atomic mass of the isotopes. So when you get all the isotopes and you average their mass, that's called the atomic weight. And further, you can calculate the molecular weight. The molecular weight, we're not going to ask you to do that. I mean, I just want you to see, the reason we are talking about atomic number, atomic weight, and things like that is that what is a proton, what is a neutron, and so forth. So you can understand more like atomic structure. Okay. Now we have isotopes versus radioisotopes. Now, isotopes may or may not undergo radioactive decay, whereas radioisotopes essentially undergo radioactive decay. So radioactive isotopes are unstable, and they have a nucleus or nuclei that spontaneously decay over time to form other isotopes. Okay. So these are, something for your information only, but isotope facts. So all elements have isotopes, just so you know. There are 2 main types of isotopes. We have stable isotopes and unstable isotopes. The ones that are unstable, they're known as radioactive isotopes. There are about 254 known stable isotopes. Okay. All artificial lab-made isotopes are unstable and therefore radioactive. Scientists will call them radioisotopes. Some elements can only exist in an unstable form. For example, uranium. Hydrogen is the only element whose isotopes have unique names. So deuterium will be hydrogen. So deuterium for hydrogen with 1 neutron, and tritium is for hydrogen with 2 neutrons. Okay. Now, carbon occurs naturally in 3 isotopes. We have carbon-12, we have carbon-13, and we also have carbon-14. Okay. So in here again, for your information only, you can see that radioisotopes can be used for radioactive dating, okay, which is a technique used to date materials. And we can see tritium, which is hydrogen-3, right? You can see it here. And that emits beta radiation. And the half-life for that radioisotope to decay is about 12 years. Carbon-14 emits also beta decay, beta radiation, and the half-life for carbon-14, it's 5,730 years. It is used here, you can see the use here. So archaeological dating, the age of carbon-containing organisms. You can see potassium. We can see, for geological dating, okay, potassium. So you can find the age of rocks and minerals, okay. Phosphorus, for radiotherapy in leukemia, cancer therapy, cobalt-60, tenectium, for diagnostic purposes. You can see the gamma radiation is emitted by this type of radioisotope. Also iodine-123, there is also iodine-131, which can also be used, emitting, by the way, gamma radiation as well. And it's also used in thyroid therapy. And in nuclear reactors, we have uranium, okay? And now we're using, with Elon Musk, we're using nuclear energy to propel the rockets, okay? So a lot more powerful technology, okay? So let's continue. If you want to know more about, how carbon-14, for example, is used in archaeological dating, you can watch these two videos down here. The second one is actually explaining the process that you see here, okay? And this one is more simplistic, simplistic, this first video here. So again, I'm not going to ask you to calculate the half-life or anything like that, but you can see how radioactive isotopes can be used in, it can be used for, like, for example, archaeological dating, right? For diagnostic procedures, okay? It can be used for as a form of therapy. It can also be used for deep space exploration, So at the end of the day, what I want you to know is what is a radioisotope, or what is an isotope, for example. What is an isotope? So these are atoms of the same element with the same number of protons, but different number of neutrons, okay? And you need to understand, atomic structure. You need to know that electrons, surround a nucleus, okay? I kind of always make the analogy, when we look at an atom, that, students that are closer to me being the nucleus, there is not going to be any interference in between me and them. We're very close to each other. But those students that are all the way to the back, that sit all the way to the back, there's a lot of interference. People talking in the middle. I try to minimize that, but people might be whispering to each other, and you might be more disengaged from the class, and more disengaged, and you might lose interest in the class because you're not hearing well, you're not understanding well, and you tend to react with something else. So it's kind of like the same idea that we're going to be discussing very shortly when we talk about bonds, chemical bonds. But back to radio isotopes. They're also known as radionuclides. Now, weakly radioactive isotopes, they emit gamma decay, okay? And they're used for diagnostic procedures. So you probably heard about tenectium, thallium, iodine. So, when they do a thyroid scan, a brain scan, a scan of the heart, things like that. So in nuclear energy, we're talking about, sorry, in nuclear scans, okay? Nuclear scans. Because we have CT scans with or without contrast. They have MRI as well. They have nuclear scans as well. Nuclear scans, radioactive isotopes. Okay, so notice that a less strong radioactive isotopes, they emit beta decay. Now, beta decay is stronger than gamma decay. So beta decay is used for therapeutic procedures, like to kill cancer cells. Okay, and if you want to kill the organism, if you want to kill the person, you give them a strongly radioactive isotope, which emits alpha decay. So people that work in with in a nuclear reactor that uses uranium and things like that, that can being exposed to radiation. I mean, their hair might fall off, their nails might fall off, their teeth might fall off. It's I don't want to be in that situation. Okay, but here is a someone they're doing a nuclear scan. Maybe they're doing a nuclear scan here of the liver or a specific organ. Okay, and it uses a gamma camera that captures this decay. And you can see, once you take the picture, it's digitalized. Once it's digitalized, then you can see the tissue that where these radioactive isotope was most absorbed. The tissue that absorbed most of the radioisotope. So usually, with nuclear scans, we study the anatomy and the function of the organ or the tissue that we are examining. Here, if there is an enlarged thyroid gland, you can have a lot of an abnormally increased uptake of this radioisotope. And you can see another part that might have a decreased uptake of the isotope. So the tissue might not be very functional, or it might be too functional. Okay, so it's kind of like that idea. Okay, so you can see how chemistry applies to anatomy and physiology, or to the study of anatomy and physiology. And you can see here, I found this image, and you can read through this, but you can see that nuclear imaging shows organ and tissue structure as well as function. Okay. There is the most common type of detector of this decay is a gamma camera. Okay, and you can see that areas where the radioisotope was taken most will be considered a hotspot. Okay, so these are kind of like terminology that they use with when they do a thyroid scan. So you can see like hot spots, and cold spots. Okay, so you can see, you can read through this, so you can have a better understanding of how this is used in the medical field. Okay, so all of that information that I just explained, you just need to know atomic structure, that in the nucleus of an atom, we have protons and neutrons, that this nucleus is surrounded by a cloud of electrons, which are negatively charged. So, and also we need to know what an isotope is. Now here, this table shows you the principal elements in the human body. You can see that they're listing the elements, the percent of the total body weight that these elements contribute to. So you can see that oxygen, again, 65% of the body weight. So oxygen is in every molecule pretty much, you know. So you can see calcium here, 1.8, okay, percent of total body weight, okay. It's the most abundant, calcium is the most abundant mineral, but it's not the most abundant element, okay. So you need to interpret that. And you can see the significance of these elements, okay. I think we need to pay attention to always like calcium, sodium, and potassium. Calcium, potassium, and sodium. You can see that they, based on the description, it says calcium found in bones and teeth, but it's important for membrane function, nerve impulses, muscle contraction. Potassium, important for proper membrane function, nerve impulses, muscle contraction. Sodium, important for membrane function, nerve impulses, muscle contraction. So you need to know, you know, pretty well, you know, like calcium, potassium, sodium. You know, there is trace elements here as well. And there is iodine here, which in AMP2 you're going to learn that is needed to make thyroid hormone. You know, iron is needed to bind oxygen. Okay, it's found in hemoglobin. You can see it says here, an energy capture. Look at that. What are they talking about here? Iron is needed for energy capture. They're talking about the mitochondria. They're talking about the inner mitochondrial membrane. Their proteins that are pigmented. The pigment can be iron, or it can be copper. Okay, copper. Where are you, copper? Copper is here, one of the trace elements. All right, so again, these, you know, copper and iron can be used to capture energy. You'll see that in AMP2. The professor needs to make you aware of that, you know, he needs to make you aware of that, show you what that is. You know, so as we go along, we are going to learn more about like magnesium. Magnesium is the most abundant cofactor in our body. So a cofactor for many enzymes. For enzymes to work, they need cofactors. And the most important cofactor in enzymatic reactions is magnesium. You need to know that for the exam. Okay, so you can see nitrogen found in proteins. Okay, there is a nitrogen balance that we need to maintain in our body. And you're gonna learn about you know, transamination and deamination reactions in AMP2. Where in transamination reactions, we are recycling nitrogen, and in deamination reactions, we're eliminating excess nitrogen. So, you know, it just depends how you interpret the information. Okay, so keep an eye on that, because a lot of times you're taught to memorize and not think, and it's important. That's why I'm doing what I'm doing, okay, to help you think through this process, to really learn things the right way, and you can find meaning in anatomy and physiology. Okay, so carbon is found in all organic molecules. All right, phosphorus is important to make high energy compounds like ATP. Okay, phosphorus is also found in bone and teeth, and it's found in nucleic acids. Nucleic acids, DNA and RNA. That includes DNA and RNA. All right, so let's move on. Okay, so here back to atomic structure. So we can see that we have hydrogen. This is hydrogen 1, right? Hydrogen 1 doesn't have any neutrons, remember? So hydrogen 1 has 1 proton. So that means that it has 1 electron. But that energy level, that first energy level, must be occupied by 2 electrons. Well, we see that in helium. You know, we saw that in helium, right? So in helium, we see that helium has 2 protons, so you must have 2 electrons here. So helium, again, is a noble gas. But this one here, it's going to be reactive. It's not happy. This one is happy. You know, the first energy level is occupied by 2 electrons. This one doesn't have that. So if you look at lithium, lithium has 3 protons in the nucleus of the atom, Okay, it says 3 protons here, right? So if you have 3 protons, it must have 3 electrons. The first energy level is occupied by 2 electrons, and then we can't fit the other one. So you have to create another energy level. And we put that electron here in the second energy level, right? But that second energy level must be occupied by 8 electrons. And lithium only has 1. It needs 7 more. It's like, oh, how am I going to get 7? Or it may lose these electrons. It's easier to lose this electron or share it with somebody else. I don't know. But it wants to become stable because he's not happy. But both of these are unhappy. But if you look at neon, another noble gas, and neon has 10 protons. Okay? So you put 2 electrons in the first energy level, and then the next 8 in the second energy level. And both energy levels are filled up. They're fulfilled. So this one is happy. This one is not. Okay. Now, the outermost electrons here, the outermost electrons, in this case, this is the outermost. This is the outermost. The outermost electrons, we call that, they're in the valence shell. So we call those valence electrons. Valence electrons. And those electrons that are further away from the nucleus, they're the ones that determine the reactivity of an atom. Okay? These valence electrons determine the chemical properties of an element, okay? So that means that they determine bonding. Now, just something of general knowledge that you need to know is that the strongest bonds are covalent bonds. We're going to talk about bonds now. So covalent bonds are the strongest bonds, followed by ionic bonds, followed by hydrogen bonds in van der Waals, okay? So again, we're going to talk about covalent, ionic, and hydrogen bonds. Okay, covalent, the strongest bonds, chemical bonds. Let's move on. Let's talk about ionic bonds. Okay, we're not going to start with covalent bond. Okay, we're going to start with ionic, which is the second strongest bond here. So ionic bonds result from the transfer of electrons. So when electrons are being transferred from one atom to another, we form an ionic bond. Okay, so the key word here is transfer. So if you hear the word transfer, electrons are being transferred from one atom to the other. That is an ionic bond that is going to form. So usually this happens between a metal and a non-metal. Okay, here is a sodium chloride, which is table salt. Now sodium has how many protons? 11. Okay, chlorine has 17 protons. I told you that there's specific ones that you need to know. Like sodium has 11 protons. The atomic number is 11. And chlorine has 17. The atomic number of chlorine is 17. Now, when you put on the electrons here in the energy levels, you can see that for sodium, since it has 11 protons, it must have 11 electrons. So the first 2 occupy the first energy level. The next 8 occupy the second energy level. So 2 and 8 is 10. And we need 1 more, which is 11. So the last energy level is occupied by one electron. So he's unhappy. He's like, this energy level out here needs to be occupied by 8. And I only have 1. So I'm not stable. I'm not happy. Notice that it doesn't have a charge either. Sodium with no charge, right? Now, chlorine has 17 protons, so it must have 17 electrons. So it's like, okay, I'm going to put them in here. So the first energy level, 2 electrons. The second energy level, 8 electrons. And the next 7 occupy the third energy level. So it's like 7, I need 1 more to be happy. And he's like, sodium, come on, man. If you give me 1, I'm happy. And if I take 1 from you, you'll be happy. You'll drop an energy level and you'll be happy. So he's like, okay, we'll do that. So you can see that sodium is going to lose an electron to chlorine, right? To chlorine. gonna lose an electron. So sodium loses one and chlorine gains one. So if you lose electrons, you become oxidized. It's like, bro, you just become oxidized, you know? But if you gain electrons, you become reduced. Like, how if I gain, I become reduced? Yeah, you're gaining negative charges. You're getting reduced here. But being reduced means that you have more energy. Okay, so the more electrons you have, the more energy you have. So I mean, chlorine is a bigger atom. You know, we're gonna look at the periodic table in a moment. But you know, 11 against 17, right? Now, so notice that when an electron is passed to here, to this other atom, then sodium lost negative charges, so becomes positive. It's more positive. So now this is a cation, a positive charge ion, or a positive charge atom is a cation here, and a negative charge ion is known as an anion. Okay, so now we call this a sodium ion, and we call this a chloride ion. We're not calling this chlorine anymore. This is a chlorine atom. This is a chloride ion. Okay, and since both of them have opposite charges, they attract. And what type of bond do they form? An ionic bond. Done. Ionic bond is a transfer of electrons from one atom to the other. If you lose electrons, you become oxidized. If you gain electrons, you become reduced. There is a mnemonic which is called oil rig. Oil rig. So with oil rig, if I can right here, oil rig. You know what an oil rig is? Those oil wells in the middle of the ocean, right? So oil rig means that oxidation is losing of electrons, and reduction is gaining of electrons. Reduction is gaining, oxidation is losing. So who lost? Sodium. Sodium became oxidized. And who gained? Chlorine. Chlorine became reduced. You need to know this for MP2. Oxidation and reduction. You need to know what that means. Okay? And, you know, I investigated all about salt, you know, unrefined salt, such as sea salt, refined salt, which is table salt, and there is iodized salt, which is enriched with, which is basically refined salt with enriched with iodine. So iodized salt is what I get, you know, to it's good for your thyroid. All right, the other ones that are unrefined, there might be contaminants in it, you know, so like heavy metals, for example. There is Himalayan, you know, like some type of pink salt as well. But again, that's unrefined. All right, so I need to erase these. How do I erase? Where is the eraser? Here is the eraser. Let me erase this oil rig from here. All right, so let's continue. Now, this is the Pauling scale. The Pauling scale has to do with electronegativity. Electronegativity. This is important to understand ionic and covalent bonding. Okay, so as we move across the periodic table and up, that is increase in electronegativity. So the most electronegative here, you know, these are the noble gases here. It's going to be fluorine here, fluorine. But you see, chlorine is here. Notice that electronegativity of chlorine is 3, and sodium is 0.9. When you subtract the difference between these two numbers, if it's 2 or more, okay, you form an ionic bond. If the difference is 2 or more, you form an ionic bond. So you can see that if you subtract 0.9 from 3 is going to be more than 2. So you form an ionic bond. So between sodium and chlorine, an ionic bond forms. Okay. We're going to see other bonds here. Now we're going to go into covalent bonding. Covalent bonds. Covalent bonding results from sharing of electrons. And you can share a pair of electrons, you can share 2 pairs of electrons, you can share 3 pairs of electrons. If a pair of electrons is shared, you form a single covalent bond. If 2 pairs of electrons are being shared, you form a double covalent bond. And if 3 pairs of electrons are being shared, you form a triple covalent bond. Okay? So covalent bonds, with covalent bonding, the atoms must be very similar. Okay? So for example, or they might have, or they should have an electronegativity difference of less than 2. If it's less than 2, you form covalent bonds, which is sharing of electrons. So we have 2 hydrogen atoms here, they're the same. So they have the same electronegativity. So they share electrons. So one hydrogen atom has 1 electron, and the other hydrogen atom has another electron. Says, you know, we need to fulfill our first energy level. And so if we get together here and we share these electrons, we can fulfill that. It's like, yeah, that's a good idea. And you form what? A covalent bond where electrons are being shared between atoms that are the same in here. The same goes with oxygen. Oxygen. So when you go to the periodic table of elements, what will be the atomic number for oxygen? I mean, if you count the number of electrons here, 1, 2, 3, 4, 5, 6, 7, 8. So it's 8. So the atomic number of oxygen is 8. Look in here. Going back to the periodic table of elements. The atomic number for oxygen is 8. So oxygen has 8 protons. So it must have 8 electrons. So 8 electrons, right? So I'm going to put 2 in the first energy level, and I'm going to put the next 6 in the second energy level. But the second energy level needs to be occupied by 8, not 6. So it's like, so this atom here gets together with another oxygen. It says, you know, you have 6 just like me. If we share, electrons here, if I share 2 of mine and you share 2 of yours, then we can be happy here. Okay, so how many pairs of electrons are being shared here? 2 pairs of electrons, and you form a double covalent bond. So here's an oxygen molecule, right? Hydrogen molecule, right? So the 2 atoms are the same, but they are unstable, so they need to gain stability here, and they do that by sharing electrons. Okay, and since they are the same the same atoms, right? They're sharing electrons equally. You know, if electrons are being shared equally, it is not like it's like more of a pull from an atom. You know, like one atom is not pulling electrons to itself. I mean, like all of them. I mean, they have the same pull because they have the same strength, right? So oxygen on this side is pulling over here, and the other one is pulling on the other side. Right? But it is non-polar. There is no polarity because they are the same. They have the same strength. So they're non-polar covalent bonds. Okay, they form a non-polar covalent bond. So these here are non-polar covalent bonds. Now look at carbon dioxide. You're like, wait a minute, Professor. Now we got different atoms here. What's going to happen? So carbon is the atomic number for carbon. What is it? Okay, 1, 2, 3, 4, 5, 6. So it's 6. Okay, for oxygen it's 8. Remember, 8. but for nitrogen is different. But for carbon, the atomic number is 1, 2, 3, 4, 5, 6. I'm counting like the gray atoms here. So the atomic number is 6. So that gives me 6 electrons. So it's like, you have 6 electrons. You're gonna be in the middle, okay? I'm a bigger atom here, so we're gonna be on the outside here. Unlike the big brother here, protecting you with the big brothers here. So, so this one again has 1, 2, 3, 4, 5, 6. So yeah, 6. So for carbon, right? For carbon, it has 6 protons, so it must have 6 electrons. So we put 2 in the first energy level, and then we put 4 on the second energy level. But it's like 4 on the second energy level. I need to have 8. I need 4 more. So it's like oxygen is like, I got you covered here. Okay, I'm gonna share 2 of mine. You share 2 of yours. The other oxygen says, I'll share 2 of mine, you share 2 of yours, and we're all gonna be happy. Okay. So, and notice that because of these double bonds, this is a linear molecule. That means that there's going to be a pool of electrons to this oxygen atom. There's going to be a pool of electrons to this other oxygen atom. So their pool are going to be canceled, okay? Because they have the same strength, one side and the other. So again, carbon dioxide is because of the structure that is linear, it is non-polar. It's a non-polar molecule. So you can see the examples here, okay? Non-polar molecule. So oxygen and carbon dioxide are non-polar molecules. That's an important concept for you to understand in anatomy and physiology. Here's nitrogen. Nitrogen, the atomic number for nitrogen, what would it be? So I'm going to count the 1 here. So you have 1, 2, 3, 4, 5, 6, 7. Okay, so let's see. Carbon is 6, atomic number. Nitrogen is 7, and oxygen is 8. Let's visit the periodic table once again. So here's the periodic table of elements. So you can see that oxygen has 8, the atomic number is 8, nitrogen is 7, and carbon is 6. So we're talking about nitrogen here. So you have 7 protons, so we must have 7 electrons. 7 electrons. Okay, so I'm going to put them here. So the first 2 occupy the first energy level. And then we need 5. So we put 5 around here. But then we need 5, 6, 7, 8. We need 3 more. We need 3 more to occupy that second energy level. 3 more. So it's like nitrogen. He talks about another nitrogen atom here. It's like, look, if I share 3, you share 3 of yours, and we'll be happy. Like, okay, we'll do that. We'll form a molecule. And since the 2 atoms are the same, this again is, now we're going to find, we're going to form 3 pairs of electrons here. So 3 pairs is a triple covalent bond here. It is non-polar because the 2 atoms are the same. They have the same pool of electrons. Now we get over here and we have nitric oxide. Nitric oxide. Nitric oxide is a vasodilator, by the way, because it's vasodilation. And it can, vasodilation lowers our blood pressure, right? So nitric oxide. So we have nitrogen and we have oxygen. And he's like, okay. So let's see here. So oxygen has the atomic number is 8. So he has 8 protons. So you got to put them in here. So if you have 8 protons, you must have 8 electrons. So the first 2 occupy the first energy level, and the next 6 occupy the second energy level. But it's like, wait a minute, I need 2 more to fulfill this energy level. I have only 6, I need 2 more. So he's like, talks to nitrogen here. He's like, nitrogen, if I share 2, can you share 2? He's like, I'll do that. I'll make you happy. But man, I'm not going to be happy here because, I need 1 more. Oxygen is happy. if you count all of the electrons here, it's going to be 8 now. But if you count the ones for nitrogen, you have 4, 5, 6, 7. And it's like, I need one more. And I don't have it, so I'm unstable. So this is a molecule that is unstable. And we called this a free radical. A free radical is an atom or molecule that doesn't have their orbitals filled. I mean, their energy levels filled. So free radicals, they are the strongest. I mean, they're not the strongest. The strongest oxidizing agents are like, the strongest free radicals are like viruses. They destroy things. That I remember that. But it's not like a virus is not like a chemical. But the thing is that free radicals, what happens is that they want to become stable. So they're going to steal an electron from somebody. So if they steal an electron from somebody to gain stability, they're going to make somebody else unstable. And that's how they damage cell membranes. And by the way, free radical damage can shorten your life, can make your life shorter. So if you have a lot of free radical damage, you're not going to live long. You're not going to live long. So we need to neutralize these free radicals. We need to neutralize them. So free radicals are oxidizing agents, meaning that they will steal an electron from somebody, right? And they'll become reduced, right? So if you steal electrons, you become somebody oxidized. So you're an oxidizing agent. So you oxidize and you become reduced. And the one that becomes oxidized becomes, has less energy, and it might not do the proper function. So it can cause damage to cell membranes. So we need antioxidants. So to treat free radical, to minimize the damages by free radicals, we need antioxidants. Okay, and that's why we take antioxidants. Now let's talk about let's talk about something else. Well, let's continue. We need to know two definitions here. What is cohesion and adhesion? These are properties of water that describe how water molecules interact with each other and other things. So cohesion is the attraction between water molecules, while adhesion is the attraction between water and other substances. Okay, so cohesion is responsible for surface tension, as you see here with this water strider right on top of the water. So surface tension, which causes water to form beads on wax surfaces. So now we're going to see how what happens. Let me see. I don't want to run out of battery here. So okay. So let's see. All right. So let's look at water. What type of bonds do we find in water? And what type of bonds do we find between water molecules? And what type of bonds do we find in water? So water is H2O. Okay, H2O. So 2 hydrogens and 1 oxygen. Okay, so now notice that oxygen, the atomic number of oxygen, the atomic number is 8, right? So that means that the first two, so if we have the atomic number is 8, that means that we have 8 protons, so we must have 8 electrons. The first 2 occupy the first energy level, and the next 6, the second energy level, but you need 2 more. So it will interact with hydrogen here, and you'll form a covalent bond. By the way, how do I know it's a covalent bond? Look at the Pauling scale. Here's hydrogen, and here is oxygen. Oxygen, the electronegativity for oxygen is 3.5, and for hydrogen is 2.1. When you subtract those two numbers, the difference is less than 2. And if it's less than 2, you form a covalent bond. Okay. All right, so you form a covalent bond here. So these are covalent bonds. You know, in water, we find covalent bonds in a water molecule. But oxygen is a bigger atom than hydrogen. So it's going to pull the electrons towards it. So you're going to form a polar covalent bond, Okay, polar covalent bond. Okay, polar covalent bond. It was the same thing with this one here, by the way. This one is a polar covalent bond as well. Nitric oxide is, you form a polar covalent bond. You form polar covalent bonds. But in carbon dioxide, you form non-polar covalent bonds. In water, you can see here as another example of polar covalent bonds is water. Water has a band structure, and you have single bonds. So oxygen will pull electrons from the hydrogens. So the part of the hydrogens is going to be, it's going to be less. It's going to have less electrons. That electron is going to be moving. It's going to be pulled towards the oxygen. So the oxygen is going to be more energized here, more negative, because the electrons are spending most of their time with oxygen and less time with the hydrogen. That's why you see the plus signs here, and you see the negative sign over here. Now, what type of bond do we find between water molecules? Okay, so an oxygen from a water molecule, and a hydrogen from another water molecule, they're going to form a bond here. It's going to be an attraction here. And we call this bond a hydrogen bond. So a hydrogen bond is different than a covalent bond. A covalent bond is between the hydrogen and the oxygen in the water molecule. But between water molecules, the bond that you form between water molecules, between one water molecule and the other water molecule, that's called a hydrogen bond. Hydrogen bonds, they increase, they create surface tension, okay, and they slow the rate of evaporation. So that is important, okay. The ability of water to resist shift in temperature is due to its high specific heat capacity. Water's high specific heat capacity is due to the hydrogen bonds between water molecules. Okay, so that's so it slows the rate of evaporation, right? Or it resists the shift in temperature. So that's a property of water here. That's like learning more about water. Now we're gonna learn about what happens if you put a solute in water. Okay, so let's see what happens with that. Now, water is an effective solvent, okay, because of its chemical structure. Many inorganic compounds undergo ionization or dissociation. In this process, ionic bonds are broken as individual ions interact with positive or negative ends of the polar water molecules. And the result is a mixture of cations and anions surrounded by water molecules. We call that hydration spheres. So, all right, so now this is, here you can see sodium chloride. I wanted to, show you, and this is glucose. So we have an inorganic molecule here, sodium chloride, in water. You can see that it ionizes or breaks apart, into the corresponding cations and anions. You can see that the cations here, like sodium, is going to be attracted. Sodium is positively charged, right? So it's going to be attracted to the oxygen, which is negative, oxygen in the water. And then chloride being negatively charged is going to be attracted to the hydrogens in water. You form like hydration spheres here. You can see here glucose being surrounded by water, by water molecules, okay? But notice that glucose, which is made up of carbon, hydrogen, and oxygen, it's not being broken up, broken apart like in the individual atoms, so you don't see that. It's an organic molecule. So I wanted to find an image that would better explain that. So you can see here a sodium chloride crystal, like table salt. Okay, and you can see that when you put water, when you add water to table salt, it will dissociate into their corresponding cations and anions. Okay, so here's sodium and here's chloride, and you form hydration spheres around it. Now, if you have a sugar crystal, table sugar is sucrose, by the way, then sucrose will come apart from the crystal, and it will be surrounded by, eventually, sucrose will break into two, and you'll form fructose and glucose, and it's going to be surrounded by water. But the whole molecule will be there. The whole glucose molecule or sucrose molecule will be there. Okay. So here's the difference between a solution, a homogeneous mixture, a suspension, a heterogeneous mixture, and a colloid. And it tells you here specific examples of what they are. You can read through it. Okay. A solution, by the way, is a mixture of a solute and a solvent. A solvent and a solute. But it can be homogeneous, it can be heterogeneous, or it can be a colloid. Okay. This is sucrose, by the way, surrounded by water. It was in a crystal, right? Sucrose. This is like table sugar. You can see that it's separated by water into sucrose molecules. Okay, so hydrogen bonds. Hydrogen bonds, you want to know that they are weak polar bonds. So they're weak bonds. Okay, hydrogen bonds are weak bonds. I want you to know that they're found in water, that they're found in the secondary structure of proteins, and they're also found in nitrogenous bases, in nucleic acids between nitrogenous bases. So yes, for now, we already saw, hydrogen bonds in water, but in the organic chemistry chapter, you'll see how hydrogen bonds are important in the secondary structure of proteins, and how they are important in attaching nitrogenous bases in DNA and RNA. Disulfide bonds are covalent bonds, okay, and they're non-polar covalent bonds. So these are strong bonds, and you find them. They're important they play an important role in folding and stability of some proteins. For example, like antibodies and keratin. You can see disulfide bonds here in holding or stabilizing an antibody molecule. You can see it also in disulfide bonds in keratin. All right. So let's talk about chemical reactions. There are different types of chemical reactions. So there is a synthesis reaction, and there is there's decomposition reactions. So you're gonna learn about metabolism. You're gonna learn about metabolism later in AMP2. So in metabolism, you'll see anabolic reactions where bonds are being formed, and you're going to see catabolic reactions where bonds are being broken. Okay, So if you're forming bonds, that's a synthesis reaction. Okay, so you have like two reactants here, and you're forming a product. So you're going from simple to complex. That's anabolism, from simple to complex. That requires energy, by the way. To form bonds, that requires energy. And to form a bond, you need to remove water. So when you remove water, that's called a dehydration synthesis reaction or condensation reaction. So these reactions here, dehydration synthesis reactions, they require energy. Decomposition reactions, chemical bonds are being broken. So you go from a more complex molecule to simple components, right? So you're breaking a bond. To break a bond, you need to add water. So if you add water, this is called a hydration synthesis. So if you add water, then you break the bond. So this hydration synthesis or hydrolysis reaction, a decomposition reaction. So for the exam, make sure you know this equation here and that equation here. Pay attention to the equations. So you can see here that you're forming something complex in an anabolic reaction. And in a catabolic reaction, you're breaking bonds. Okay, and you're going from complex to simple to simplex. An exchange reaction, known as also as the displacement reaction, you're going to have decomposition first and synthesis after. So you're going to have catabolic and then anabolic. Okay, so an exchange reaction. So you first break and then you form. You break and then form. I found an image here that shows you that. For example, here is adenosine triphosphate or ATP. So here's ATP and here's glucose. So when glucose is transported into the cell, then energy is being invested. So you break a bond, a phosphate bond, and you add it to glucose. So you break a bond, decomposition, and then you form a bond, synthesis, right? So this is what we call an exchange reaction. You have decomposition first, you break a bond, and then you form a bond after that. So the reason a phosphate is added to glucose is to trap it within the cell. You can see here, again, that in decomposition, you're breaking something more complex into smaller components. This is like glycogen, how we store glucose in the form of glycogen. So during fasting, we can break down glycogen into glucose. And here you can see like amino acids, which are the building blocks of proteins, So we have something simple to make something complex. So this is a synthesis reaction. Okay. And then lastly, we have a reversible reaction. A reversible reaction. A reversible reaction is a reaction that occurs simultaneously in both directions. A plus B yields AB, or AB yields A plus B. So if you have this arrow that it goes in opposite directions, that goes like in both directions, right? That is a reversible reaction. All right. So that is with respect to chemical reactions. Those are the ones that we covered in AMP1. Synthesis reaction, decomposition reaction, exchange reaction, and reversible reaction. Now we're going to talk about enzymes. Now enzymes, I mentioned that enzymes are important to, for reactions to occur much faster and most effectively. So what enzymes do, they lower the activation energy, the energy of activation, which is the energy required to start up a reaction. Without an enzyme, and by the way, enzymes are proteins, okay? And they're protein catalysts. They speed up. A catalyst is something that speeds up a reaction, okay? So here's the activation energy without an enzyme. If you don't have an enzyme, the activation energy is a lot higher. But with an enzyme, we can lower the activation energy in red here, we can lower the activation energy and make this happen, okay? I just want you to know that enzymes, they participate in a chemical reaction, okay, but they're not changed or destroyed, okay? So they're not changed or destroyed, but enzymes are affected by changes in pH and temperature. So enzymes, they work at a specific pH and at a specific temperature. So that's important. So enzymes are protein catalysts that lower the activation energy, you know, so that the reaction is more likely to happen. Enzymes, they need cofactors. The most important cofactor is magnesium. Okay, they're not used up or changed in a reaction, and they can be affected by changes they can be affected by pH and temperature. Okay. Enzymes, they also have a specificity of binding, so they bind to specific substrates. They also have a specificity. They also have saturation limits. So if something is already bound to them, no one else can bind. And they can also be regulated. They can also be regulated by other factors, okay? So these are characteristics. Okay, so this slide is very important for you to know, okay? Cofactors, again, magnesium is the most important. You know, for the HESI exam, which is the entrance exam for nursing, you need to know what cofactors are. You need to know what a proenzyme is, what a coenzyme is. So they have prosthetic groups, they have apoenzymes, holoenzymes, isoenzymes, all kinds of stuff. This is for your information, okay? But I need to know that a more important cofactor for enzymes to work is magnesium. Then we get into exothermic and endothermic reactions, okay? This equation here, make sure you know it, okay? Make sure you know these equations here. On exams, they usually ask about these equations as well. So when the energy is on the side of the products, it's an exothermic reaction, and that means that energy is given off. Energy is given off, okay? Like if you're burning wood and heat is released into the environment and you're getting warmed up, you know? Okay. Endothermic reactions, the energy appears in the side of the reactants, okay? That means that energy is being absorbed. It's being absorbed from the surroundings, like melting of ice. If you leave ice out here, it will melt because the temperature surrounding it is it's higher, and the ice will melt. Okay, so combustion of fuels, exothermic, melting of ice, endothermic. Okay. Now here's a question in chemistry: why water is never added to an acid? Never add water to an acid. Add acid to water, but not water to an acid. If you did that, then an exothermic reaction can occur, and heat can be liberated, and there can be an explosion. Okay, actually that happened in our medical school. I mean, I was looking at a video back. I was thinking back about the medical school that I went to, and there was actually an accident an explosion in the lab. So it must have been something similar to this. So add acid to water, but not water to acid. Also, vapor rub. I don't know if you know the mechanism of vapor rub, but when you're congested, putting vapor rub on your chest can help you feel like your breathing has improved. It does this by releasing menthol vapors that feel cooling to your nasal passages. This tricks your brain into thinking you're breathing more easily. I don't know if you know that, but keep vapor rub, keep it away from your face. You can put it in the chest, maybe in the neck area, chest. Sometimes they put it as far as the bottom of your soul. But that smell is going to trick your brain that you're breathing easier. Okay. So, and I think, I bring Paper Rub in here. Big's Paper Rub is an exothermic reaction. Now, these are potential energy diagrams. I'm not going to ask you about this in the exam, but this is something that can be asked on the HESI exam. So they can show up. They might show you a graph. This is like more like physics in a way, a little bit, or inorganic chemistry, perhaps. Yeah, inorganic chemistry. And that's why I have it here. Okay, but notice that this is the potential energy. Okay, so here's the potential energy. Notice the potential energy is higher here than the reactants. I mean, it's higher here than the products. The reactants are here, and the products are here. So here is the energy of the reactants, and this is the activation energy. They always ask you about delta H. How is delta H? The change in enthalpy, change in enthalpy in an exothermic reaction. It will be negative. Delta H will be negative. So if the energy of the reactants is higher than the energy of the products, you will see that energy will be released. Okay, so energy will be released because you have more potential energy here. Energy is being released. Exothermic energy is being released. So you see that energy is in the side of the products. Okay. If in an endothermic reaction, the energy of the reactants, the potential energy of the reactants here are lower than the energy of the products, and therefore delta H is positive. That means that energy is being absorbed, and that means in an endothermic reaction, the energy will appear in the side of the reactants. Okay, so all right, so that's how that works. But in here, there is a video that is very good. You can watch that video if you want to have a better understanding of these graphs here. Here's a sum up, of the both exothermic and endothermic reactions. Okay, you just want to know, the exam might be as simple as asking you, where do you find the energy, on the side of the products or in the side of the reactants? If it's on the side of the reactants, that means that is an endothermic reaction. An endothermic reaction. So endothermic reactions, delta H is going to be positive. Okay, energy is being absorbed. But exothermic reaction, delta H is going to be negative. So energy is being released. This is, there's just an exercise for you to know, like, for example, what type of reaction do you see here? Where the reactants are lower, the potential energy of the reactants are lower than the products. Is that endothermic? Is that endothermic? Right? And then what about if the energy of the reactants are higher than the products? That's going to be exothermic. Okay, so exothermic reaction, endothermic reaction, exothermic reaction. In general, it's going to be exothermic. Okay, so delta H, in exothermic, you release energy, delta H is negative. Okay, you see that here. Delta H is negative. Okay, and I gather this information for you, but I'm not going to ask you in the exam. Okay, when you go from like ice to water, that's melting, and that is endothermic, which delta H is positive. You see that? When you go from liquid to gas, you have to add heat here and heat over here. So again, delta H is positive. That means that this is an endothermic reaction. Heat is being taken. okay, by the system here. So this way is endothermic. The other way is exothermic. When you go from solid to gas, sublimation, that will be endothermic. By going from gas to solid, deposition, that is exothermic. You see that? So you never know. You never know if they're going to bring any of this stuff, on an exam, for example. I'm not going to do it to you, but I think that you should be learning this stuff here. Aqueous solutions, electrolytes and body fluids. Okay, electrolytes and body fluids. Oh, by the way, I brought the same YouTube video here that you saw over here. I brought it over here because he goes over this as well. So electrolytes, you need to know the definition for electrolytes. Electrolytes are soluble inorganic molecules whose ions will conduct an electrical current in solution. So electrolytes are soluble inorganic molecules, right? Like sodium chloride, whose ions will conduct an electrical current in solution. Like see here, sodium chloride, that's an electrolyte. And when you put it in solution, it will ionize or dissociate into their corresponding cations and anions. And since they have charges, they can conduct an electrical current in solution. Potassium chloride is another electrolyte, and so forth. Okay. You know that when somebody is having vomiting and diarrhea, you can have an electrolyte imbalance. Or if somebody is taking like diuretics, like somebody who's retaining fluids, and he's taking a pill that will make him pee, that's a diuretic, you can deplete potassium, and you can also be create an electrolyte imbalance. People like that are on diuretics, depending on the diuretic, if it's a potassium sparing diuretic, like a spironolactone, you don't have a problem with that. But if you're taking Lasix, furosemide, then you might, you're going to lose potassium. You need to eat a banana every other day, and every 3 months, I think you're supposed to check with a physician for a blood test to see how your electrolytes are if you're on diuretics on a daily basis. Hydrophilic and hydrophobic compounds. Okay, hydro means water, philic means loving, phobic means fear. So compounds that like water includes ions and polar molecules, like water. Okay, ions and polar molecules. Compounds that hate water or fear water will be non-polar molecules like oxygen and carbon dioxide, fats, oils, and waxes. Okay, we need to know this for the third chapter. Okay, when we talk about the cell. Here's the pH and homeostasis. pH stands for potential hydrogen. So it is the concentration of hydrogen ions in solution. A hydrogen ion is not the same as a hydrogen atom. A hydrogen atom has an electron. A hydrogen ion doesn't have an electron. A hydrogen ion is also known as a proton. A positive charge hydrogen is a hydrogen ion. The more you have of those, the more acidic the solution is going to be. Okay. So what is the potential hydrogen? If I have a lot of hydrogens, acidic. If I have less hydrogens, probably it's going to be basic. Okay. So let's look at the pH scale. So here's the pH scale. So you go here from 0 to 14. But usually, 1 is like extremely acidic. 7 is neutral. 14 is extremely basic, right? Or alkaline. 7 is neutral. So if there is a higher concentration of hydrogen ions, then it's going to be more acidic, the solution. If the solution has an increasing concentration of hydroxide ions, It's going to be more basic. Okay. There is a video here, right on top here, that talks about these numbers here. Like what is 10 to the minus 7, which is actually a pH of 7. Okay, you see here, pH is equals negative log of hydrogen ion concentration. And the negative log is 1 in 10 million, okay, 1 in 10 million, which is a negative log of the concentration of 10 to the negative 7. And that's the pH of 7. They talk about these things here, more in a little bit more in depth. And they talk about acid rain and how that affects our oceans and the coral reefs and the species that we have living in the water. But for us, we need to know that a pH that is less than 7 is acidic, and it has higher concentration of hydrogen ions. And a pH that is higher than 7 is basic because it has a higher concentration of hydroxide ions. Okay, and you can see here, like for example, if you like Coca-Cola, classic Coke, that's acidic. Coffee, acidic. Tomatoes, grapes, acidic. Pickles, wine, vinegar, beer, acidic, right? Notice the blood pH. Blood pH is slightly basic. It ranges from 7.35 to 7.45. So it's slightly basic. Okay. You can also see urine pH. Urine pH goes from like 4.5 to 8. Okay. So it has a broad pH here. Urine. Okay, and so now I want you to know the pH, pH scale here has an inverse relationship with the hydrogen ion concentration. So for example, let me do this here. pH is inversely proportional to the concentration of hydrogen ions. Okay. So the more hydrogen ions you have, the lower the pH. A low pH has a high concentration of hydrogen ions. A low pH has a high concentration of hydrogen ions. If the hydrogen ions are low, the pH is high. So that's what we call an inverse relationship with hydrogen ion concentration. That is important for you to know that concept. A lot of students miss this on the exam. So a solution that has a pH of 5 has more hydrogen ions than a solution that it has a pH of 6, for example. Okay? So you need to understand that. All right, so let's continue. An acid is a proton donor. So it would add hydrogen ions to a solution. Remember, add acid to water, not water to an acid, right? Strong acids completely dissociate in water. Okay. A base removes hydrogen ions from a solution. It's a proton acceptor. So if you add a base, you can remove hydrogen ions. So strong bases dissociate again in aqueous solutions. So remember, a base removes hydrogen ions. An acid or lowers the concentration of hydrogen ions. An acid adds hydrogen ions to a solution. A weak acid or weak bases, they don't completely dissociate in water, and they help to balance pH. So they act as buffers. A salt, they dissociate into cations and anions when they're put in water. So salts, like sodium chloride in water, they dissociate into sodium and chloride. Okay, so they form neutral compounds. Buffers, you need to know the definition for a buffer. A buffer, these are compounds that stabilize the pH of a solution by removing or replacing hydrogen ions. So just know that buffers, they stabilize the pH of a solution. If you want to know more about buffers, you can watch this YouTube video here. But there is 3 buffer systems that help us to maintain pH. The most important is the carbonic acid bicarbonate buffer system. That's the most important buffer in the extracellular fluid. But just know that buffers are compounds that stabilize the pH of a solution. Okay, you're gonna learn that later, but not now. Antacids, these are basic compounds that neutralize an acid and forms a salt. So antacids, they form a salt and they neutralize an acid. And examples of antacids, you can see rolates or tums. Those are antacids. You can have other examples of antacids here. Antacids, the chronic use of antacids, that's not good because it neutralizes the pH of your stomach and it can lead to problems. Okay, so the stomach pH needs to be acidic because when you eat, there might be things in the food that need to be killed by the acidic pH. And if you neutralize it all the time, that's not going to be good. And if you form a salt, that's not good for that creates a state of alkalosis, and it can lead to other problems. You can see that also it can impair the ability to digest and absorb certain nutrients. It also increases the vulnerability to infection. Okay, and it reduces the bioavailability of some drugs as well. It affects the absorption of drugs. So, to relieve heartburn, a lot of people take antacids, which neutralizes an acid. But there's other ways, to reduce the amount of acid that is being produced. We can use proton pump inhibitors like omeprazole, or you can use an H2 receptor antagonist like famotidine or Pepcid. But again, I think that you need to take other measures and avoid taking medications. So don't eat too late, don't eat too fast, don't drink water with food, don't eat, don't spend too much time not eating and having to eat so much, especially late at night when you fall asleep. And it depends how you're combining your food as well. So there's many factors that you might not be taken into account that is leading to heartburn. Okay, but that is the first part. Okay, so it's all about inorganic chemistry. Okay, and in class we can we can kind of like highlight some important concepts here to make sure that we understand, especially like the difference between ionic bonds and covalent bonds, and the different types of chemical reactions, the importance of enzymes and what they are, the cofactor magnesium, exothermic and endothermic reactions, because that can show up, especially with these, potential energy diagrams, how this is represented. Again, you can watch this video. This is very important. And these are some important facts about exothermic reactions and endothermic reactions. Exothermic, they release heat, so delta H is negative. But in endothermic reaction, you gain heat, so delta H is positive. So these are things that you need to keep in mind. Okay, these things, this is like stuff that you learned in the past, in high school. Now, we want to keep that, present. You don't want to lose that. You want to have a better understanding of these concepts. Electrolytes, okay, the pH scale, hydrophobic and hydrophilic compounds, oxygen and carbon dioxide. What do you have? You have, these are non-polar covalent bonds that you find here. So these are non-polar molecules that can diffuse through the phospholipid bilayer in the cell membrane. That's an important concept. That's how you link chemistry with actual, anatomy, physiology. All right, so we'll leave it here and see you on the next recording.